You ever stop to think about what a super rigorous, abstract mathematical proof could possibly have to do with a practical, down-to-earth computer program? I mean, on the surface, they seem like they're from completely different planets. But today, we're going to pull back the curtain on a hidden connection that ties them together, a secret that has totally reshaped both of their worlds.
All right, so let's just dive right in with the big question. What does a mathematical proof really have in common with a computer program? Now, it sounds like a riddle, right? But the answer reveals one of the most profound ideas in modern computer science and logic. It's not just that they're similar, it's that they are, in a very deep way, the same thing.
You see, this hidden link isn't just some clever analogy. It's like discovering a shared language, a Rosetta Stone, that lets us see logic as a kind of computation and computation as a form of applied logic.
And that unifying concept, the key to this whole thing, is the idea of types. Whether you're talking about classifying data in a program, like an integer or a string of text, or you're trying to structure a logical argument, the concept of a type is the bridge that connects these two universes. It's the language they both speak.
Okay, so let's get to the heart of it. How does this connection actually work? This is where we get to the core idea, this paradigm of proofs as programs.
The official name for this is the Curry-Howard isomorphism. Now that sounds pretty intimidating, I know, but the idea behind it is just stunningly elegant. It says there's a direct, one-to-one match between proofs in a field called constructive logic, where proving something means you actually have to build it, and programs in computer science. They're not just alike, they are two sides of the exact same coin.
And listen, this isn't just some minor academic detail. As the source material puts it, this connection forms the real backbone of the relationship between these two fields. It is the absolute foundation that everything else we're going to talk about is built on.
And this table just breaks it down perfectly. So check this out. On the logic side, you have a proposition. That's just a statement you want to prove, like a plus b equals b plus a. Well, in the world of computation, that's your type, like number. Okay? Now what about the proof you build to show your proposition is true? That corresponds directly to a program that computes a value of that type. The proof literally is the program. And the final piece? Simplifying a proof in logic is the exact same process as running the program.
So what this really means is that a logical proof is no longer just some abstract argument you scribble on a whiteboard. The Curry-Howard isomorphism gives it a computational reality. It turns a proof into a living, breathing object that you can actually execute and interact with, just like any other piece of code.
Now you can imagine, this idea had a massive impact, and it started with the very foundations of mathematics itself. It gave mathematicians a totally new way to think about truth and proof.
And this wasn't some overnight discovery. It evolved over decades. It started with early work like Russell's theory of types, which tried to dodge paradoxes in logic. Then came the big one, the Curry-Howard isomorphism, which made the proofs as programs idea official. That led to incredibly powerful systems like Martin Löw's type theory, which was a huge leap forward because it treated proofs as actual mathematical objects you could play with. And today, that journey continues with some seriously mind-bending stuff like homotopy type theory.
So what did all this actually do for math? Well, for starters, it gave us a powerful new toolkit for formal reasoning. By turning these abstract proofs into concrete proof objects that you could actually work with, and by organizing everything into these consistent hierarchies, it made the entire structure of mathematics stronger. It even connected these new ideas back to established foundations like set theory.
All right, so let's cross that bridge to the other side and see how all this played out in the world of computer science. This is where all those abstract logical ideas become the real-world tools that build the software we use every single day.
In programming, type systems are, well, they're everything. They're not just there to catch silly little errors. They provide the fundamental structure for our programs. They're an incredibly powerful tool for guaranteeing that our code is correct. And they even let us formally reason about how fast and efficient our code is going to be. And you can see its fingerprints everywhere. The entire paradigm of functional programming, built on this. You get advanced features like dependent types, which allow a program's type to check for, say, mathematical correctness. This means we can prove that bugs are absent before we even run the code. And even common things we take for granted, like polymorphism, code that can work on many different types of data, it all has its roots right here.
This deep connection enables something that sounds like science fiction, automatic program synthesis. The process is just so logical, it's beautiful. You start by writing a formal proof that a certain property holds. That proof becomes a real proof object. Then, because of the Curry-Howard isomorphism, that object directly translates into a working program that is guaranteed to have that property. You're literally generating correct code from pure logic.
And the power of type theory goes way beyond just correctness. It lets us analyze how a program will behave. By putting certain rules inside the type system, we can guarantee a program will run at a specific time, meaning we can write code that is provably fast, not just fast in our tests. It even lets us analyze more complex things, like the probability of different outcomes in randomized algorithms.
So, after seeing both sides of this incredible correspondence, what's the big takeaway? What does this all really mean for the future of logic, math, and computer science?
Well, the first and most important thing is this. Logic and computation aren't just related. They're not just cousins. They are two dialects of one single fundamental language. This completely changes the game. It transforms a proof from just a philosophical argument into an engineering object. It's no longer a static chain of reasoning on a piece of paper. It's a dynamic process you can run, test, and execute. And believe it or not, this idea is still evolving in some pretty wild ways. Modern research in areas like homotopy type theory now suggests that a proposition can be understood as a kind of geometric space, the homotopy type, that's defined by all of its possible proofs. It just shows how deep this connection really goes.
Which leaves us with one final, pretty provocative question to chew on. If a proof of a mathematical truth is in fact a computer program, that changes everything. It opens up this amazing new frontier where the act of discovery and the act of computation become the same thing. So it forces us to ask, what new truths are out there, not just waiting to be proven, but waiting to be computed?